Uh, Good day. Welcome to my video. Now, in this video, we're gonna do grade 11 Euclidean geometry. So before we can even start, make sure that you understand your basics very well from the previous grades. In previous grades, you have learned the line that intersects to form many different types of angles. We're talking about the alternating angles, we're talking about the corresponding angles, we are talking about the co-interior angles, we are talking about the exterior angles and the interior angles, all of that. And therefore, you have also learned the properties of your quadrilaterals, such as the parallelograms, what's happening with their angles, if the sides are like this. You have learned all of those things, and you have also learned different types of triangles. You have learned the isosceles, the scalene, the equilateral triangles, and you know what's happening with the sides of those triangles and the interior angles. You have also learned about the similarities. You have learned about the congruency. All of those things that you have learned in the previous grades, they are most definitely still applicable even today, okay? So now here in grade 11, we're gonna do the Euclidean geometry based on the circles, okay? The circles, we're gonna learn about how to calculate the angles, how to do many things regarding that, but you'll see as time goes by, okay? So now let us start with the session of Euclidean geometry. Now what you see over here, it is a circle, okay? So now in Euclidean geometry, most of the times you're gonna be told that in this circle, you are given the center of the circle. So when you are told that the circle has a center, that's very important. That's very, very important, okay? Because we can talk about many things coming out of the center, okay? So now let us start with the basic terminology that I believe you need to understand, okay? So now with Euclidean geometry, a line that is drawn from center to the circle, okay? Or a line that is drawn from center to the circumference of the circle, it is called the radius of the circle, okay? It is called the radius of the circle. A line that is coming from center to the circumference of the circle, it is called the radius. I know we all know that, right? And now, a line that is drawn from the circumference to the center, and then from the center again to the circumference of the circle. Now this line, it is called a diameter, okay? It is called a diameter of the circle, okay? A diameter, it is made up of two radii, meaning a radius from this to there, a radius from this to the center, a radius from this to the center. The combination of these two radii that makes an angle of 180 degrees, which is a straight line, we're gonna call it a diameter, okay? Now, say we have a radius and a radius, meaning we have two radii, okay? So now, these two radii, within these two radii, within this portion, the pizza-shaped like structure, we're gonna call this portion a sector, okay? We're gonna call this portion a sector. So now when you talk about a sector of our circle, we are talking about the region bounded by what? Bounded by two radii and arc of the circle. We have two radii, and then we have the arc of a circle. It's a sector, okay? And therefore, we have what we call a chord, okay? So a line from circumference to a circumference, we're gonna call it a chord of a circle. So don't confuse a chord and a diameter. Remember, diameter is supposed to pass through a center from chord to, from a circumference to a circumference through a center. This is a diameter. But from a chord, from a circumference to a circumference, this line, it doesn't pass through a center. It is called a chord of a circle, okay? And then this area over here of a chord that is subtended by a chord and the arc of a circle, we're gonna call it a segment, okay? We're gonna call it a segment, okay? So now a line that passes through a circle like this, where it cuts our circle at 2 points. And I want you to pay attention to this line. This line, it gets out of the circle, okay? Now, this line, we're going to call it a secant, okay? We're going to call it a secant. Don't confuse a secant and a chord. A secant, it projects out of the circle, but a chord, it ends within the circle from circumference to the circumference of the circle. But a secant, it is most definitely going to project out of the circle, okay? So that's what you call a secant. So a secant and a chord, they are all they are a little bit the same, okay? All right, I hope that it is making sense. So now these are the basic terminologies that you need to familiarize yourself with. And then the last line that I'm going to talk about, it will touch your circle only at one point, okay? So let me try to draw it. It's going to be a little bit complicated for me to draw it, but let me just draw it. It's supposed to touch my circle only at one point, okay? Here it is. So I'll just say here we have a point over here. It's a point of contact, okay? So now look, this line, it's not supposed to touch your circle at 2 points. The line that touches your circle at 2 points, it is called the secant, like I said, okay? I can draw my secant over here, whereby it's going to touch my circle at 2 points. So this line, it's supposed to touch your circle only at one point. And what is the terminology for this line? We're going to call it a tangent, okay? This is very important, guys, a tangent. So now these lines are very important when we're going to prove the theorems and then apply the very same theorems. They're going to help us to do what? To do some problem, to be able to solve some problems, okay? So here we have a tangent, which is a line that touches your circle only at one point, okay? It is a tangent. It is not a secant. Don't confuse a tangent and a secant. Don't confuse a secant and a chord. Remember, a secant, it projects out of the circle. As much as a tangent, it is out of the circle. But the difference between the secant and the tangent is that the tangent touches your circle only at one point, okay? All right. So now, let us continue here. So these are the basics that you really need to familiarize yourselves with, okay? Don't confuse these basics. Now, we move on to the theorem. Now, what you see here on the board, it is theorem number 1, okay? So now theorem number 1, it reads as follows, okay? So we say theorem number 1 states that the line drawn from the center of a circle perpendicular to a chord bisect the chord, okay? Now this is what is happening. We are given the circle and then we are given the lines. A line from center to this chord. Remember, this is a chord because it touches circumference to circumference. We have already learned the terminologies, right? So a line that is drawn from the center, remember, this is the center of the circle. We have center O. The line that is drawn from a center of the circle, and then it gets to intersect your chord. So where your line intersect a chord, you have to know that mathematically, this line, which is line OM, will always act perpendicular to line AB. It is a theorem. That's how it is. It has been proven by mathematicians. So you're going to also learn on how to prove this theorem, okay? So the theorem states that the line from the center of a circle acts perpendicular to a chord. And that line, as it acts perpendicular to a chord, it cuts or it bisects your chord, or it cuts your chord into 2 equal parts. So this word bisect, it simply means that a line, this line which is AM, it is going to be cutted into 2 equal parts. So that means AB. So that means AM is going to be equals to MB. B, because the word bisect means this line, it's going to be divided into two equal parts. We have bisect and intersect. Bisect means into two equal parts, okay? All right, intersect means the line, it is going to be cutted, but not into two equal parts. So if you have a line like this, and then you have let me call this line AB, and then you have a line that crosses this line. This line, we say it intersect line AB, but not into two equal parts, because this line over here, it intersects. But say, for an example, you have AB over here, and then you have a line that passes through AB. So this line, we're going to call it a bisector, because this line, it cuts your AB into two equal portions. This is intersector, and this is bisector. So bisect means AM supposed to be equals to MB. And on top of that, OM will be acting perpendicular to AB. This theorem states that. Okay? All right. So now, um, so now, so this is the reason that we are going to use, okay? When we state this theorem mathematical, I'll show you how. So we're going to use this theorem, this reason all the time. Line from sector perpendicular to the chord, okay? And we are also going to talk about the converse of this theorem. But the converse of this theorem, you're not supposed to know how to prove it for exam purposes. But I'll show you how the converse work, because you still need to know it when it comes to problem solving questions. You're going to have to give the reasons of the converse theorem, but I'll show you once more again how. All right. So now theorem number one, let us learn on how to prove it. Let us learn to know how to prove this, okay? So now in exam, this is what they're going to give you. They're going to give you a statement like this and an empty circle like this. They're going to say to you, given, you are given the circle with center O with OM perpendicular to AB. Oh, this is the only thing that is given to you in exam. You are given this circle with center O, whereby OM will act perpendicular to AB. And therefore, you are required to prove that AM is equals to MB. Look, theorem number one, we know that if this line acts perpendicular to this line, therefore this line will be equals to this line. But we have to prove that. We're gonna believe as if we do not know that AM is equals to MB. We're gonna prove that AM actually is equals to MB. Okay, we're gonna prove that. So now each and every time when it gets to Euclidean geometry, when you prove your theorems, you start with your construction. This is the first thing that you need to do when proving the Euclidean geometry. We're going to start with our construction. So now let us answer this question in exam. So how are we going to start with our construction? For theorem number one, you are going to construct in this way, okay? You are going to join these 2 points. You're going to join O and point A, okay? You're going to join O and point A. And you are also going to join what? You are also going to join O and point B. Going to join O and point B, okay? Now check, this is what is happening. After joining these lines, now we managed to form the triangles. We have 3 triangles. We have triangle ABO. We have triangle AMO. We have triangle BMO. 3 triangles after constructing our circle. So now you're going to write it in exam. You're going to tell us, what did you do? You're going to say, respectively, you're going to join OA and OB with all due respect. Respectively. Okay? This is not your second. Respect it. I'm just saying. So you're going to do that. This is the first thing that you are going to do. Okay? Now, the second thing you're going to do, it is the proof now. Now we're going to do a proving. Now you're going to prove, okay? So now how are you going to prove this? So now, this is what you're going to do. You're going to mention the triangle that you are going to work onto, okay? So you're going to say in triangle OMA, which is this triangle over here, and in triangle OMB, what is happening in these 2 triangles? Now, this is what you're going to do. Like I said at the beginning of the video, you have learned different types of triangles. You have learned all of the basics from the previous grades. So now in these two triangles, what do you see? This is what we see, okay? We can prove congruency between these two triangles. But now, how are we going to prove that congruency? Now, we can see that OA and OB, these lines are called the radii, okay? The radius are equal in magnitudes of one circle. So this circle has the same magnitudes of radius, okay, of radii. So that means we're going to start by mentioning that OA, which is the side of this triangle, because I get this side, I'm going to say everything. When I prove my congruency in this side, I'm going to mention everything regarding triangle OMA. And this side, I'm going to mention everything regarding triangle OMB. So on this side, I'm going to say OA is equals to OB is equals to BO. So why am I saying that? In Euclidean geometry, each and every time when you give the statement, you're supposed to give the reason, okay? So we're saying OA is equals to BO. Why? Because those lines are what are radii, okay? Those are our radii. So this line is equals to this line, which is radii. And therefore, we are going to say this side, which is OM for triangle OMA, and this line again, which is side OM for triangle OMB. It is the same side, it is the common side. So that means you can say OM is equals to OM, or you can just write OM, okay? So I prefer doing it like this. I'm going to say OM is equals to OM. OM for triangle OMA, OM for triangle OMB. It is the same. So what is the reason for that? It is a common side. So I'm just going to write common over here. Okay. I'm sorry about that. Therefore, remember, when you prove congruency, you need a maximum of at least 3. Okay. So we have 2 so far. And therefore, what do we see? Now, remember, we said OMX perpendicular to AB. So that means here we have M1 and then there we're going to have M2. So these angles over here, they form 90 degrees. They are both equal for both two triangles. So that means I'm going to say triangle, angle M1, M2, because this side, remember, it is triangle OMA. So angle M2, it is going to be equals to angle M1. Why am I saying this angle is equals to that angle? Simply because both of them, they're equals to 90 degrees. And it is given. Why am I saying it is given? Because from the given statement, we were literally told that OM will act perpendicular to AB. So that means for a fact that these lines are perpendicular, we know that this is 90 degrees. So that's why I'm saying this, it is given, which is 90 degrees. Okay. So now we have at least a maximum of 3. Now we can conclude that the very same triangles that we were talking about, they are congruent. Okay. So we can say, therefore, that means triangle OMA will be congruent. Okay, remember, this is for congruency. It is congruent to triangle OMB. And therefore, what is the reason? You also give the reason, okay? You OMB, so here it's supposed to be M. Please switch.
Allow Zoom to find and connect, determine the position
Please
nearby person.
switch
Allow
off the
Zoom to
mic.
find to connect to determine the relative position
Sorry,
of nearby
sorry,
devices. Bolela.
sorry,
Haka ka don't allow.
sorry.
Allow Zoom to
Thank you. So triangle OMA is congruent to triangle OMB, okay? Let me just rewrite this properly. So here we have M, okay? Let me just, where's my pen? There is Z, blue one, all right. So OMB. So now these two triangles, we say they are congruent. This is a sign that we use for congruency. But each and every time after stating that your triangles are congruent, you need to give a reason, okay? Because these guys is for marks. If you do not include all of these things, you're going to forfeit marks. So that means, what is our reason? You can say RHS. What does RHS mean? It means right angled triangle. We can see that these two triangles are both right-angled triangles. Okay, now we can simply say, therefore, for a fact that these two triangles are congruent. Remember, when you talk about the congruency, we are talking about the triangles that are the same. These two triangles are exactly the same, meaning the sides are the same. The interior angles are the same. Similarity means that the triangles have the same angles. We say they're equiangular. The sides are not the same, but are in the same proportion. That's similarity. But congruency, it means that the triangles are exactly the same. Okay, so we have proved that these triangles are the same. Now we can simply say, therefore, AM is equals to MB. AM is equals to MB, and therefore this is what we were actually required to prove using theorem number 1. I hope that was clear. If it is not clear, make sure that you raise up your hand and then you ask a question. Right. So now this is theorem number 1, okay? But now this is what I want you to understand, guys, okay? This is for exam purposes. In exam, they can ask you to do this, to prove this, okay? Which is theorem number 1. So there is what we call the converse of theorem number 1. The converse, it is not for exam purposes, but you need the basic of converse to do the problem solving. Look, converse number 1, you do not have to prove it, but you need it to apply it on some questions. Okay, now let me show you something. How does the converse work? So now, say, say you are provided with a circle like this, okay? And then you have your chord. I'm sorry about my drawing. You have your chord, and then you have your center of the circle, okay? And then you have a line that comes from the center to the chord, okay? Okay, I'm going to explain converse, okay? Once more again, you have your circle, you have your center, you have your chord, you have your line from the center to the chord. So let's talk about theorem number 1, what we have just discussed over here. Remember, theorem number 1 says, if you have a line from center, and this line is going to act perpendicular to the chord, okay? This line from center will act perpendicular to the chord of the circle. Therefore, remember, here we have A, and here we have B, and then here we have M. So if you have this, that means AM, it is going to be equals to NB. And therefore, the reason for this is this one. Line from center is perpendicular to chord. So if line from center is perpendicular to chord, that means AM is equals to MB. That's theorem number 1. Okay, I repeat for the last time. Line from center, if it acts perpendicular to your chord, that means AM is equals to MB. Therefore, what is the reason? Line from center perpendicular to chord. That's theorem number 1. The converse of theorem number 1, it says, this is what it says, the converse, okay, of theorem number 1. This is theorem number 1. This is the converse of theorem number 1, converse. It says, a line from center bisect chord. Here we have A, M, B. Ne? A line from center, it bisect chord. Ne? So here we are told that AM is equals to MB. So sometimes in exam, instead of them giving you that this is 90 degrees, rather they give you that AM is equals to MB. This is the converse of theorem number 1. So the converse says, if AM is equals to MB, that means, let me write O here. That means OM is perpendicular to AB. Okay? These two are the same. But here, what is given is perpendicular. Here, what is given, it is that AM is equals to MB. So if you are told that AM is equal to MB, that means OM is perpendicular to AB. This is converse of theorem number 1. So now what reason are we going to use here? We are not going to use the very same reason. The reason that we are going to use over here, let me change my color pen. The reason that we are going to use over here is we're going to say line from center. Ne? Line from center, you can say to midpoint of chord, or now I love saying line from center bisect chord. Okay, bisect chord. Let me change my color pen once more again. This thing is disturbing me. Okay. So now, this is the converse of theorem number 1, okay? This is the reason that we're going to use to apply the converse of theorem number 1 when we do the problem solving. You don't have to prove this. You only have to prove this, which is what I have just showed you over here. So the converse says that if you are given that, AM is equals to MB, that means OM is perpendicular to AB. Therefore, the reason that we're going to use, you're going to say line from, sorry, I was supposed to write center here. Line from center bisect chord. But theorem number 1, if you are given that OM is perpendicular to AB, then that means AM is equals to MB. The reason that you're going to use, you're going to say line from center is perpendicular to chord. I hope that was making sense. Was that clear? How to use theorem number 1 and its converse, and which reason to use? Because I've realized a lot of learners, they confuse these two. Does it make sense what I'm saying right now? Or you need clarity? Right, okay. So now let us do the problem solving that is related to this theorem, okay? So now here we have the questions, okay? So now question number 1, it reads as follows. The statement says, question number 1, O is the center. Here's the O, and then AC is equals to 8 units. So now we are told that AC is equals to 8 units, and OB, which is from here to here, line from center to the chord, we know that AC is chord. They don't have to tell us that AC is the chord. We have learned the terminologies. Literally, we know this is the chord. So line from center to the chord, it is given that line from the center is equals to 3 units. And OB is perpendicular to AC. We are also given, it is also given that OB is perpendicular to AC. Now we know that this is theorem number 1, basically, okay? So now we know that if OB is perpendicular to AC, what does that mean? Then that means AB is equals to BC, but you're going to have to give a reason. And I have showed you which reason to use when applying theorem number 1. We are not proving theorem number 1 yet. We are applying theorem number 1. So now 1.1, it says to us, calculate the length of AB. So now they want us to calculate the length of AB, which is this length over here, point A to point B. We are given AC, and we know that AB is equals to BC. So to answer question number 1.1, this is how we're going to answer it. I'm not going to take the long route. I can take the long route to answer this, but if you do not understand what I'm going to do right now, you can raise up your hand. So now to calculate the length of AB, we are going to say AB is equals to 4. Okay, this is the simplest way to answer it, not to waste time in exam. You're going to say, you're going to get your full marks. You're going to say AB is equals to 4. And therefore, why are you saying AB is equals to 4? This is your reason. You're going to say line from center perpendicular to chord. Line from center perpendicular to chord. This normally could be 1 mark or 2 marks, whereby you need your statement and your reason. So you're going to say AB is equals to 4 units. Why? Because we have line from center which x perpendicular to chord. So that means we know that AB is equals to 4, or you can say, or the long route that you can take, you can say AB is equals to BC, right? And then the reason will be why line from center is perpendicular to chord. So if you have a look at what I did over here, it's theorem number 1, not the converse of theorem number 1. I said to you, if you are given the line which is perpendicular to this, that means AB is going to be equals to BC, which is what I have just written over here. And then I say the reason that you're going to use is this one. Line from center perpendicular to chord. I'm going back. This is what I told you. Okay, this is theorem number 1. If you are given this line is perpendicular to this line, that means this will be equals to that. And then I said you use this reason. Line from center perpendicular to chord. I hope that is making sense. And therefore, you can conclude by saying, therefore, AB is equals to 4 units. Okay, that's how we answer 1.1. You don't have to say, therefore, AB plus BC is equals to AC. And then that's a long route. Okay, so you can do this or that to answer this question, which is 1.1. Now, 1.2, it says to us, determine the length of OC. So now we know here we have our 4. And then here we have our 4, which is BC, most definitely. Now determine the length of OC. OC, it is the radius, line from center to the circumference in this triangle. You have learned different types of triangles. What type of a triangle do you see over here? Right angle triangle. So to determine the size of right angle triangles, we use Pythagoras theorem. So to determine OC, you're going to say OC is equals to how much? It's our hypotenuse, right? OC, it's OC squared is equals to OB squared plus BC squared. And therefore, what is our reason? You're going to say it is your Pythagoras, in short, theorem, or theorem of Pythagoras, okay? Remember, this is Euclidean geometry. You give your statement and your reasons all the times, okay? So that means we're determining the length of OC, which is hypotenuse, which is opposite to 90 degrees. Therefore, what is the magnitude of OB? OB is 3 to the power of 2. And therefore, what is the magnitude of BC? It's 4. We have already determined that. And therefore, here we're going to have 9. And then here we're going to have 16. And therefore, what is 9 plus 16? I think it's going to be 25. We're going to have 25 over here. And therefore, remember, on this side of the equation, we have OC squared, not OC, but we are looking for OC. Mathematically, we're going to do our root sign on both sides. We introduce, remember, you do plus or minus when you introduce a root sign. But because this is hypotenuse will always be positive. So that means we don't need plus or minus. So that means what will be the magnitude of OC? It will be 5 units. Therefore, the length or the magnitude of OC, it will be 5 units. And therefore, we managed to solve question number 1.2. So this is simple. I believe you all understand this. Okay. Now let's move to question number 2. So now question number 2, it says to us, statement, O is the center. That's very important. OB is equals to 6 units. Where is OB? Line from center to the chord is equals to 6 units. And then OC, our radius, is equals to 10 units. And OB, it is perpendicular to AC, theorem number 1. You see, that means AB is going to be equal to BC. What's the reason? Line from center, perpendicular to chord, okay? Line from, oh, sorry, you're supposed to include center here. I don't know why am I like to forget the center over here. Okay, don't make that mistake. You have to include center here. Line from center, perpendicular to chord. So now, they say to us, calculate the length of AC. AC is from here to there, okay? So now, in order for us to calculate the length of AC, we need to know the length of BC first. But how? we're going to use Pythagoras theorem to determine BC literally for this triangle because we have two sides. So that means you're going to say BC squared is equals to OC squared, which is hypotenuse, subtract OB squared, which is another side of our triangle. You can write your equation in this way if maybe you feel like this will confuse you, okay? But I just hate doing things that are unnecessary to waste time in exam, okay? But if you really do not understand, remember, you raise up your hand. So BC squared is going to be equals to OC squared minus OB squared. And therefore, what is our reason? Remember, it's Euclidean geometry. You give the reasons. It's Pythagoras theorem. Okay, and therefore now, what is the magnitude of OC in this case? OC, it's 10. Can I say 10 to the power of 2? Subtract OB in this case is equals to how much? OB is equals to 6 units to the power of 2. So here we have 100, subtract 36. And therefore, what is 100 subtract 36? I think it's 64. What is my calculator? I think it's going to be 64. Let me check for my calculator fast. You know, sometimes you even punch 1 + 1 on calculator because you don't want mistakes. You don't want to lose marks over silly things, okay? So that's me all the time. Yes, it's 64. So here we're going to have 64. So remember, we have BC squared, not BC. So we're going to get rid of that. So in geometry, these our lengths. They are always positive. So that means what will be the magnitude of BC? So you're going to say root of 64 is equals to how much? Is equals to 8, right? We know that is equals to 8 units. So here that means we have 8 after using our Pythagoras theorem. Now let's determine the magnitude of AC. So now you're going to say again, you're going to say AC is equals to 16. Why? Line from center perpendicular to chord. Or you can say AC, sorry, not AC, AB. AB is equals to this side. AB is equals to BC, which is this side. Why? Literally, theorem number 1, you are told, oh, this is perpendicular to this. So you're going to say line from center perpendicular to chord. This is the reason why we're saying this is equals to that, right? Therefore, we can say that AC, which is combination of AB and BC, which is 8, 8, is going to be 16 units. You don't have to show that it's AB plus BC. You can just say it's 16 units. Okay, that's how we solve these questions.